Recapping, this chapter is about electric circuits and particularly a DC, direct current circuit, which means that you have a battery and the electrons all flow in one direction. We've talked about the parts of the circuit and how these things relate to each other in V equals IR. We took a little side path to talk about drift velocity so that you would have some idea of what the electrons are actually experiencing as they're going through the wire. And then we also talked about how you can quantify resistance with the formula R is equal to rho L over A. And now this, we talked a little bit at the very end about how the current can really affect you negatively, and it doesn't take a lot of current for that to happen. So I've got a graph here, and I'd like you to kind of pencil that in to your notes, maybe pause it if you need to. I drew it in advance just because it is a little bit complicated. It is supposed to be this way where the lines get closer and closer together as you get to a new designation. This is a logarithmic scale that you're looking at, and you'll see that what each of these different lines mean is different from the different places within the scale. From here to here, it's increasing by 1/10 of a milliamp. From here to here, it's increasing by 1 milliamp. From here to here, it's increasing by 10 milliamps. So each time these lines are increasing by a power of 10 and how much it changes from line to line. So that's a logarithmic scale, and that's how that works. Just really quickly, I'm not going to read each one of these, but you can see that you're going to just start feeling something at 300, a little bit over 300 microamps. You'll start feeling it, but at 1 milliamp, it's going to start hurting. And at some point in here, around 10 milliamps, somewhere in there, depending on your own particular resistance, you will not be able to let go. The current has clenched the muscles so that it's really painful, but you can't let go of it. And from about 100 milliamps to about 3 amps, then because this, and I should have said this from the beginning, this is what you experience if the current is going from one hand to the other hand. And the direct path it's going to follow is going to be the path through your body. And of course, that's going to lead you right through your chest cavity, including your heart. So this is super dangerous if you're holding on to wires, or somehow you're holding onto a wire and your hand is touching something that is that's a good conductor. That's going to be the path of least resistance, the shortest path, and it's going to go there. So if it travels across your torso, these are the things you can expect to have happen. That's why you would go into ventricular fibrillation, and at that point, because of that, you could die. Beyond that, if you get up to about 3, maybe a little bit higher, maybe 4 amps and above, then severe burns, cardiac arrest, death is not just possible, death is probable. So it doesn't take a lot of amps for you to experience some pretty severe effects. Electricity, not something to mess with, folks. All right, that was just my friendly warning for the day for you, my public service announcement, I guess. Now let's get into the rest of what we're doing here. The next topic we're going to talk about is resistance and how it affects the temperature of things. And you actually have a chart, the temperature coefficient of resistance, that you're going to want to have available so you can look at it while I'm talking about it. The relationship between resistance and temperature is that generally, not universally, but generally, what would you expect to have happen? As resistance increases, what would you expect to have happen to the temperature, or more to the point, I should say it the other way around, as temperature increases, what would you expect to have happen to the resistance? If the atoms, and particularly the electrons, but if the atoms are moving faster because the temperature has gone up, then that means you're providing more opposition to the flow of electrons. So as temperature increases, so does resistance, generally. Not universally, but generally. The constant alpha is called the temperature coefficient of resistance, and it tells you how every specific kind of material reacts to increasing the temperature and the resistance it provides as a result of that. So the constant alpha is called the temperature coefficient of resistance. Temperature coefficient of resistance. The formula for finding how much does resistance change is, how much does it change as you increase the temperature, is R sub T, which is the resistance now at the temperature you've raised it to, is equal to R naught, the original resistance, times the quantity 1 plus alpha delta T. Okay, so within that formula, R sub T is going to be the resistance at the final temperature, at T final. R naught is the initial, or R initial. Alpha is the temperature coefficient of resistance. And again, you're going to get that off of the chart. And then finally, delta T is your change in temperature. And that delta T has to be, so it's T minus T naught, but it has to be in degrees Celsius. And the reason it has to be in degrees Celsius is because the unit for my temperature coefficient of resistance is going to be degrees Celsius to the -1. So these numbers were created based on Celsius degrees. They were measured based on Celsius degrees. So again, what we're doing here is we are looking at the effects of changing temperature on the resistance of a circuit. And interestingly, this can actually be used practically because if I know how much the resistance changes, I can also work backwards and find the temperature. And that is called a resistance thermometer. And that's what we'll be talking about in this next piece. A platinum resistance thermometer has a resistance of 100 ohms when placed in an ice bath at 0 degrees Celsius. A geologist lowers the thermometer, a resistance thermometer, into the hot springs, and the resistance raises to 123.5 degrees Celsius. What is the temperature of the springs? So I'm going to write down what I know and what I don't know. My resistance at the final temperature is 123.5 ohms. Hate making this symbol. 123.5 ohms, and then my R naught, my original, is 100 ohms, and remember that was taken at 0 degrees, so that's going to be my T naught. And alpha for the ice bath, or alpha for water, do I know that? I'm sorry. No, I'm sorry. It's not for the substance it's in. It's for what it's made of. And so alpha for the platinum resistance thermometer, I'm sorry, that was a bad moment, is 0.00392. And that's degrees Celsius to the -1. And then my delta T is what I'm looking for, because my delta T is going to be my final temperature since T naught is 0. So my formula, R sub T is equal to R naught times 1 plus alpha delta T is equal to 123.5 is equal to 100 times 1 plus 0.00392 delta T. Now, remember with this, let me kind of talk you through. You guys are pretty good at this, so I shouldn't necessarily have to. And I probably don't have to, but just to make sure, I'm going to go through how I would unpack this. Okay, I want to work my way. I want to be able to solve for delta T, so I've got to move everything else away from it. Rather than getting rid of my parentheses by distributing, I would first move this over so that I'd be left with 1 plus. Then I would move over my 1, and then finally I would divide by 0.00392 to get delta T. And when you do that, delta T is equal to 59.9 degrees Celsius. And since delta T is T minus T naught, and T naught, so my 59.9, is equal to T minus 0, then T is equal to 59.9 degrees Celsius. And that's pretty much all we're going to cover today because the next section is a little bit long and I don't want to do both in one day. So you get kind of a break today. This is a nice short section. And the homework for this is going to be 21 through 23 and 25. 21 through 23 and 25. All right, let me know if you need anything.